Here's the detail. Here, the density refers to the density of this differential element. Well, by definition, the differential element is very small. So I can continue to shrink it, make it half on this side, or 1/10, or 1/100th, or 1,000th, to where this essentially represents a point in space of which the density is only at that point. And as such, I'm not making any assumption about the density being a constant in this entire derivation. For simply the fact is the definition of a differential element. Yes?
Why is it that both f and a are negative?
Say again, I'm sorry, say again?
Why is it that both f and a are negative?
F and A, okay, so you want me to go through this in some detail? Okay? So for the S direction, which way is positive? To the right, right? And the N direction, which way is positive? N. How is N being defined? First is the normal. What normal? Inward or outward? It's the outward normal. It's always pointing up, outward. Here's my radius of curvature. And that outward normal is my positive N direction, right? So why do I have a minus sign here? Which direction is the acceleration when you have a particle swinging in a circle? Outward or inward? Inward. By how much? By how much? V squared over R, pointing in the negative direction. So that's the first minus sign. Questions? How do I get the second minus sign? The forces on this differential element in the N direction will be pressure. Pressure P pointing up on the lower surface, right? What about the upper surface? Which direction will it point? Down. Towards the control volume, always. Down. And of a magnitude of P plus delta P. Yes?
Why is it that P is on the bottom and P plus delta P is on the top and not the other way around?
Okay, that's a fair question because I have choose my positive N direction going up, meaning that as I march in the outward direction, I will have P plus an incremental increase in P because I'm going in my positive N direction. So it's P plus del P. Does that make sense to you? Anyone else? Other questions? So with that, yes?
So is the delta P for like the change in height or?
It's, the delta P is the change in pressure due to a change in the N direction, which happen to be the height, but I don't want to read it that way. The same token in the streamwise direction, which is this equation, this is the change of pressure relative to a small change in the streamwise direction. So as I march down along the streamline from point S1 to S2, there is a change in pressure due to how much I move. And likewise in the N direction. All those are very good questions. And you are doing very good to slow me down. So keep coming, because this will be repeated in a month, except then we'll do a three-dimensional ball, X, Y, Z. The same basic. The building block of which is what we did way back, 2 lectures ago. Differential calculus. This is differential calculus. And this could be dx, could be ds, could be dn, could be dy, could be dz. All right, fair enough. So any question on how this comes about? I'm missing the algebra here, of which you pull all this together, F equal to ma, and bam, this final equation comes. And for the next 10, 20 minutes, I'm going to look at this equation qualitatively. And you'll answer some of the previous homework assignment we have. But do you get it? Do you understand all this discussion? Are you comfortable? Any other question? Very good, okay. So let's see how I may use that normal direction equation to learn some higher homework problem. So remember this free jet that we talked about, where you're always told as a given, if I have a garden hose with water coming out from the garden hose, that within the jet the pressure is always ambient. Or if I have an air nozzle, the air coming out from the nozzle is also have ambient pressure inside. Why is that? We will try to answer that by way of this equation of Euler equation in the n direction. So I've sketched a nozzle. In order to use this equation on my left qualitatively, I need to sketch or draw by my intuition a set of streamlines that I think will be representative of the fluid coming from through this nozzle and exiting to the outside. Right? So my intuition tell me that the flows become, and follow the shape of the nozzle, which is helped to confine the flow and accelerate it. So it exits with a streamline straight and parallel. Now, all these are idealized situations. You know from experience, sometimes when you turn on the water faucet, the flow not always do this, but 9 or 10 times it does. Watch it next time. And at some point, the water will break, but that's totally a different analysis due to gravity and so forth. So we are pretending and assuming, due to the shape of the nozzle, flow is coming out straight and parallel. Do you agree with that? Make sense? So on this diagram, where the streamline is straight and parallel, what is that radius of curvature? So here, let's say streamline become straight and parallel due to the shape of the nozzle. So I have a set of infinite straight lines. What is the radius of curvature for a straight line? 0 or infinite? It's infinite. It's infinite. Right? If they were in a circle, then I have a radius of curvature of r. But if they're straight and parallel, then r becomes infinite, such that 1 over r become what? Become what? 0. So if 1 over r becomes 0, this term is 0. Am I right? This term, 1 over r, is 0. The entire right-hand side must be 0. Got it? So what that said is the pressure cannot change in the direction of n. So Fn, my nomenclature, which will be used more and more often, represent that it's a function of. So pressure is a constant, is independent of the n direction, the normal direction, right? So on the edge, the very outermost streamline, which is exposed to atmospheric, PA is the same as P atmospheric. The outer edge, the one that is in contact with the ambient, that's stagnant air, is atmospheric. What I will conclude, within the jet, top to bottom, all the pressure is the same. If I have 14.7 at the bottom, it has to be 14.7 across the entire jet. Just for the fact because the streamline are straight and parallel. So that, I think, helps answer one of the given problem condition that we always say, if I have a free jet, pressure within the jet, inside the jet is atmospheric. And with the Euler's equation in the normal direction, that offers an explanation. Question on that? So from now on, it's no longer a given. From now on, you can argue that for a free jet, I know the pressure must be atmospheric. The second application has to further illustrate how lift, upward force, is generated on a wing. So last time, what you were told a priori was that the velocity on the top here is always faster, whereas the velocity at the bottom is lower. That was one of the problems given prior to look at velocity distribution as a given in the problem statement. That you were told if I'm flying at 280 miles per hour, the velocity due to the shape of this airfoil must be faster, say 350 miles per hour on the top, and lower, say 200 miles per hour in the bottom. You were given that in the problem statement. And then we use Bernoulli and argue that pressure on this airfoil must be higher at the bottom. Why is that again? Bernoulli, P plus half rho v squared is a constant, right? So as the velocity drop, pressure pick up, and vice versa. And the difference in pressure gives us the vertical force. All right, that's what we did. Do you have any question on that argument? Because I'm going to drop that. I'm going to say, let's don't use that. Let's don't use that. Let's see if I can argue, or rather convince you from the streamwise, from the Euler's equation in the n direction, I can show you, without having to give you the velocity, I can show you that indeed a vertical force called lift has to be generated. And that's my intent. Do you understand this backdrop or this background? Any question? So this faster flow can be such that, and this is totally a sidetrack, nothing to do with what I'm discussing. Even for an airplane flying at below the speed of sound, like 0.9 or 0.95, cutting through air, let's say F-18 is flying subsonic. But the flow accelerated on the upper surface, that at time, by the time it reached the maximum curvature, the velocity can become supersonic, let's say Mach 1.2. You can generate a shock on the upper surface. So there's some poster or picture you see of the delta wing fighter airplane that under the right condition, a cloudy day, have a vortex or a sheet of rotating swirling flow on the wing. That's what that is. A shock due to the acceleration of the flow from subsonic to supersonic sitting on the wingspan, and you can actually see what the flow is doing. All right, next time you see the poster of that, at least you can understand the origin of it. So forget all this. Now I'm going to say, I'm going to try to answer the question of how an airplane can lift up from the ground simply by this equation. And to do that, I will have to first sketch or draw or imagine the flow pattern of the streamline around this airfoil. All right? So we have one similar to what we did with the automobile in the wind tunnel problem. There one streamline that will always end up hitting the nose of the airfoil, and what happened to that streamline? It stops. So this point where it stops, we call it what? Stagnation point. Stagnation point. Velocity is zero. It's like me running at 300 miles per hour, short that wall, and I stop. And then the trailing edge, there's also a streamline that leaves tangent to the angle of the streamline. Sorry, tangent to the angle of the metal surface at the trailing edge. Beyond that, the rest of the streamline follow the shape of this airfoil. And then when I'm far, far away from the airfoil, like half a mile away, what does that streamline look like when I'm further away from the airfoil? Straight. I don't even feel the presence of the streamline. Do you agree with this flow pattern? If I can release some dye or some smoke upstream of the airfoil and let that carry with the flow, this is what I expect to see. Any question on that? Okay. Far away from the airfoil, I have my ambient pressure and the velocity at the ambient also. So I'm going to show you from this equation how I can explain the pressure on this lower surface has to be P infinity plus, meaning higher. That's my goal. That's my goal. And because the pressure, this plus sign meaning greater than atmosphere. So if I'm 30,000 feet, the ambient pressure is 10 psi, for example. This pressure must be greater than 10 psi. How much greater is depending on the shape of the streamline. It could be 12, could be 10, sorry, could be 12, could be 15. And the more curve there is for the streamline, the higher this pressure is. My goal is to show you why. And because of that, we call this lower surface pressure sign, PS. Lower surface is a layman term. We as a mechanical or aero engineer, we call this the pressure surface, or the pressure sign. All right, are you ready? To see how all this works in reference to this equation? Okay, so tell me on the right-hand side, remember, this is my n direction. Do you agree that this right-hand side with the density and the velocity is greater, and the radius of curvature is defined by that circle, is always positive? I cannot have a negative density. Velocity squared itself is always positive. Radius of curvature, the way we define it, pointing outward in the n direction is always positive. So my hands are bound. This is always a positive quantity. You see that? Right? So if I have a separate diagram, just to illustrate that, from this, as a consequence, if I draw a sketch of a streamline in a circle, by radius of curvature pointing down, outward normal is n, if I have pressure P on the lower side, according to this equation, when I move outward, away from the center of my curvature, this pressure has to be greater. When I go in the direction of positive N, the outward direction, according to this equation, the pressure must go up. Got it? Now I apply that argument to this diagram. Where down below the undisturbed streamline, where it doesn't feel the passing of the airfoil, half a mile away from the airplane, I have P infinity on sea level static, that's 14.7. What will be the pressure on the underside, the lower side of the airfoil? Less than, equal to, or greater than 14.7. Has to be greater than. So I have established an argument on the lower half of this diagram. If I'm 14.7 in the undisturbed ambient air, under the airfoil, I have to go higher, just from the shape of the streamline. Do you see that? Do you see that? And the more curved, more airfoil, just for the sake of argument, if my airfoil is like this, and the more curved my streamline, according to this equation, the higher the pressure underneath on the lower surface of the airfoil. So if I can design airfoil with this shape, this will be very desirable. Yes?
Wouldn't you get turbulent flow if you were to do
That is something we'll discuss now. So what this is very idealized, it's very idealized, simple-minded, qualitative analysis of this airfoil. So first, what is a turbulent flow? This is an ME21 pipe flow review. What is a turbulent flow? When you say turbulent, what does it mean to me? Huh? How is that different from a laminar flow? Chaotic. The flow is very chaotic. It's random. It's just very somewhat on small scale, very unsteady. That will happen for a bad airfoil design in the sense that the flow, quote unquote, separated, which is what this guy will do. So you've never seen an airfoil on a 787 look like this, because the flow cannot negotiate that sharp turn. It will separate and create turbulent flow. And all this break down. There will be no lift, and the airplane will plummet. Right? But on an idealized situation, like the airfoil is very, very mild in turning. All the airplane airfoils, at most 10 degrees of turning from the inflow to the exit flow. For that reason, that I want to keep the flow attached. That it follow the shape of the airfoil. If it doesn't, all hell break loose. So an F-18 in a dogfight at 45-degree angle, like this, the flow is not attached. It cannot continue to fly like this forever. It will plummet. All right? For a short time, couple of seconds, the momentum carry it. But you cannot fly like this steady state. The plane had no lift. It will drop. Yes?
Based off the argument you were saying earlier, where the further along the radius of curvature you go, the higher the pressure, wouldn't that mean that above the airfoil is a higher pressure, so you wouldn't have any lift as you push?
No. Let's focus on the lower part first. When I go to the upper part, it happened to be the reverse. And what happened then is, since you asked, I'm going to show you momentarily the pressure on the upper surface is not P plus. It's going to be P minus. But one step at a time, because this is very sometimes hard to visualize. So I wanted to stop and say, do you agree with me with what happened on the lower half? Let's do that first. Let's don't worry about the upper half. Because if you don't understand this, you won't understand the upper half. Do you agree with the pattern of the streamline that we draw? And according to this equation, the flow pattern will dictate, will force me to conclude that the pressure on this lower surface must be greater. Do you agree with that? Do you get it? Do you get it? Questions? Okay, very good. So far, so good. So now if I could have done it on the same sketch, but maybe just to help you to visualize. Let me redo the same argument now on the upper surface, where now I'm focusing on the streamline on the top. So let's don't worry about the lower half because we're done with it. And when I go far, far away from this airfoil on the upper side, like half a mile, the flow will not see and feel the presence of that airfoil, and it has to be, for that far away streamline, straight and parallel, which is P infinity. Same as the lower one. Right? So here's the airfoil. On this upper streamline pattern, show me which is the direction of positive N. Up or down? Go back to this diagram. How do we define that normal direction? It's normal and what? Outward. On this pattern, my radius of curvature is down below. Which way is outward? Up or down? Look at this. It's up. It's always outward, outward, outward. That's what I mean by outward. Away from my center and normal. Do you see that? That's important because if you don't see that, I cannot finish my argument. It's all on the same page? All good? So if that's the case, and when I'm half a mile away, I'm at 14.7. And outward normal is pointing up. And according to this equation, the further out I am, the pressure must be greater, because as I march in the direction of positive N, pressure has to increase according to the Euler's equation. And how much increase is not our argument now. I don't care how much. I just want to make sure you understand it's increasing in the positive N direction until I'm so far away I see 14.7. But what is then the pressure right above my upper surface? Less than, equal to, or greater than 14.7. It's got to be less than. Smaller. How much smaller is the shape of the airfoil? And how fast you go. Do you see this counter argument on the upper surface? One at a time. Lower surface, we all agree, you're convinced. Now the upper surface. And the key is the outward normal is still pointing up. And as I march in the positive N direction, pressure must keep going up. Yes?
Could you explain again that part of why is it that as you go in the positive N direction, pressure keeps going up?
That is from here, which has nothing to do with the streamline. This is the equation for your homework. And when I look at the right-hand side, can the density be negative? No, I have not ever seen a fluid with a negative density, right? Velocity squared is always positive. The radius of curvature by definition is positive, always. It's just the radius from the center to the streamline. So all count together, this term must be positive, can never go negative. Okay, so we're taking advantage of this observation to try to explain why the pressure in the jet is ambient and why pressure on the airfoil is always higher, hence the word pressure side, on the lower surface, and why is it always lower? And hence the word suction, suction, creating a vacuum, suction sound on the upper surface. All from this equation of Euler and the pattern of the streamline. Just qualitatively, you see how all this put together. Yes?
So in the equation, is R is a constant, right?
R is the radius of curvature, which is different for each of the streamline,
Okay, yeah.
right? So if I have a circle, the radius curvature is the same.
Okay. That
So,
equation gives you-
so if I have a straight streamline, like we did with the jet, this is a streamline. This radius of curvature is infinite. If I have a circle, this is my radius of curvature. If I have a pattern of streamline that each one is different, then each one at each point has its own radius of curvature.
So if you had like a turn in a pipe
Yep.
with a constant radius,
Yep.
would that equation give you like the pressure gradient?
Yes,
across
it
the-
does, and that's another very good fluid mechanics problem. So when the flow go around a band, like in the river, it set up a pressure gradient, just like what we have discussed. It does, it does. And that flow pattern creates some erosion of the river band, because this flow actually creates some circulation, right? Okay, I'll give you a 2 minutes break. I think that's all very good question. I'd like to come back and touch on the homework.